Here we go. All right, to repeat myself, we're going to do some review today on Exam 4, Chapter 6 and 7, for the exam that we have next week on Tuesday. All right, so like I always do, I want to be sure and cover anybody's concern. So I ask you first, if during your review you found anything that gave you trouble, we need to attack right now, so that we don't wait till the end and run out of time. Is there anything in particular that we need to look at? It doesn't matter if you have to go all the way to the end, to the more difficult stuff, we'll pick it up. And if there's time, we'll come back to the other things. Yes. Let me see. There's, I think this one has different levels. Some are 1 point. Then we have some 5 point. There must be some 3 points in here too. I missed those. Yep, there's some 1 points, 3 points, 5 points. On the required section, and then in the bonus section, there are 1, 3s, 5s. I think I've got a 10. No, there's a 15. In the bonus section, there's a 15 point, and the reason it's 15 is because it's in 3 parts. One part is 5 points, 5 points to the next part, 5 points for the last part. So I can't say how many questions. Well, I could say, but it won't mean much. The number of points that are part of the required section are 68. And the number of questions that represents is 24. Okay. So you can expect that the higher the points, the longer it's going to take you to solve that problem. Okay, anything we need to tackle?
I didn't really understand 15.
Okay, let's take a look at it. 15.
I don't know if it's confusing because of all the letters.
There are lots of letters in chemistry, and I don't know why that is, do you? 15. Oh, I see. Because these are generics. They're not real elements or compounds. Yeah. So let's see if we can make sense of that. So we got a reaction. Let's see. For the benefit of our video viewers, number 15. We have a reaction that is expressed generically as this. Oops, that can't be. So this represents the element or compound, and this represents the coefficient. All right, so the little a, b, c, and d, they're going to be numbers. And these are going to be either elements or compounds. That's all that means. How many values are there for a quantity C divided by D? Okay, so if you ratio this number to that number, how many possible values could there be? Well, look at it this way. What is that equal to? Let's just plug some numbers in. Let's just say, for argument's sake, that C is equal to 2 and D is equal to 3. Okay? So that would give you 2/3, right? That ratio. So once that's established and the equation is balanced, what can you do to the equation? Well, the only thing you can do after that balance has occurred is multiply the whole equation through by some constant value, either a whole number or a fraction. we multiply by a whole number, say 2, then that changes this to 4 and this to 6, right?
So why,
But it's still 2/3.
so why does it equal 2/3? Like, where did you get 2/3?
I just made it up. If you balance the equation, we could have picked something else. You know, we could have picked 6 and 4. So 6 would be here and 4 would be there. Then the ratio of those two would be what? 3/2. Right. The whole point of this question is to hammer home the concept that once the equation is balanced, these ratios are fixed. They do not change. So the answer to that question, how many possible values can there be for that CD ratio? Only one. Right? Once the equation is balanced, those numbers are fixed, and any ratios that you derive from those coefficients can only be one value. Another way of looking at it is, this is a conversion factor. If you know you have, let's stick with 6 and 4, or 3/2. Let's just make this 3 and that 2. Then if you know you have so many moles of D, let's say we have 7 moles of D. How are you going to convert that to moles of C? You need a conversion factor. So we got to have something that'll convert moles of D to moles of C. So those cancel. So what's the ratio of C and D? Well, 3 for C and 2 for D. It's a conversion factor. So it's 21/2. Or what, 7, 8, 9, 10, 10.5. It's how many moles of C you would have. If you start off with 7 here, then you have 10.5 there. The ratio is the same. It's always the same once the equation is balanced. Okay. I know it's kind of hard to conceptualize with these. So what we ought to do is work out problem with real elements and compounds. And then it might stick and drill it in deeper. Does that answer your question? There's only one possible ratio for any combination of coefficients. A to C, B to D, A to C, B to C. Any of those ratios are fixed with a balanced equation. So does anybody have a balancing problem that we need to tackle, and then we can sort of dovetail into this concept? Or do you want to just pick one?
Number 2.
Okay.
I think that was example minus.
Oh, let me see if that's worth tackling.
Or I think I did that one.
Okay, you're given the unbalanced equation, that's fine. How many moles of oxygen are required to react with one? Okay, that's fine. Yeah, we can do that one. With our present knowledge, we can solve that one. But the only reason I marked it a bonus was it was kind of out here. And I wanted you to be sure and focus on basics first. But we should be able to do that one. Right? So we'll tackle it. Because if I mark it bonus here, the only place it would show up on the test is in the bonuses. And that would be worth some, extra gravy. So if we start here, H22O11. What is that, by the way? It doesn't say, does it? Table sugar.
Yeah.
Yeah, it does say table sugar. Right? So that's the compound of sucrose sitting on your table. And then you always put too much in your tea or coffee or sprinkle on your desserts. And what are we going to do with it here? What type of reaction is that? Whenever you have oxygen as a reactant, it's a combustion, right? Classifying your reactions, that's a combustion. And what are combustions also? Oxidation reduction. A combustion has to have oxygen, and it's always a redox reaction. Okay, so this is going to produce, see, am I still picking it up? I'm good till that line over there. CO2 and water. In an unbalanced equation, I'm leaving my space in here for coefficients. Right? So what's our next step for balancing our equation? Do our inventory, right? Set up our table. So we have carbon as an element, we have hydrogen, we have oxygen. I don't see any others. Those are the only elements in here. So now we can do our tally. Initially, we start off with, on this side, 12 carbons and 22 hydrogens. And 11 plus 2 is 13 oxygens. Okay? On this side, we have 1 carbon. And we have hydrogen, 2 hydrogens. And we have 3 oxygens. Right? So that looks like a real problem child, doesn't it? Where do you start? Well, our hints, helpful hints, you want to save that one till last. Yes, did I do something wrong?
Oh, I was going to tell you where I started, but you.
Oh, no, that's fine. You be the guide.
I put the 12 I don't know.
You started with carbon?
Yes.
Okay, that's fine.
What
Go ahead.
I don't know the name of it. Like the
Oh,
CO2.
carbon dioxide?
Yes.
Yeah, we covered that in the first couple of chapters. How to name compounds.
Yeah, I get it.
Okay,
But
let's go back.
I put a 12.
Okay, let's go back to naming for a second. Where does carbon and oxygen come from in the periodic table? Carbon comes from here, oxygen from there. So you have 2 nonmetals. So is that a type 1, type 2, or type 3?
Type
3. Nonmetals are type 3s, which means you just have to name how many of them there are. Right? And for the first one, you don't say mono. Right? It's just convention. So it's carbon dioxide. That's it. Now for things like this, they have a common name, so we call it water. Right? But if we named it by our convention, it'd be dihydrogen monoxide. Okay. Okay, so we'll go back to you want to put a 12 here?
Yes.
So that gives you 12 carbons, okay. And what does that do to the oxygens? 24, and 1 is 25, right? Okay, so that gives us 25 oxygens. Okay, we got carbon taken care of. Let's look at hydrogen then. How do we get, we've got hydrogen in one place over here, that's good. How do we get 22 hydrogens from this? What coefficient would give us 22? 11, right? Okay. Now the mistake that can be made is that you say, okay, I've already got 2 here. So if I put 11 there, that's 22 plus 2 is 24. No, it's that one times that one is what's there. You're going to replace this number with that one. You're not going to add to it. Okay, so don't make that mistake. Okay, carbon, hydrogen, they're done. Now we can deal with oxygen because we left oxygen till the last. So if we can change this one, we still have to account for these 11. Don't leave those out. So what value can we put here, added to 11, will give us 25? Well, let's see.
You can put,
You need 25, right? But you've already got 11.
you can put 12.
4. So you need 14 more. Right, don't you? If I did that right.
So 7 times 2 is 14.
So if we do 7 here, that will be 14 plus 11 is 25. Okay, so that should be balanced. Let's check ourselves. 12 carbons here, 12 carbons here. Hydrogens, 22 hydrogens here, and 22 hydrogens there. That's good. So 11 plus 14 is 25. That's right. And hydrogen, oxygen, excuse me, 20. No, there's a problem.
That's what I was thinking. That would be 24, then the other oxygen would be 11. The 11 on the left side would cancel out with the 11 with the water. And you can multiply the O2 by 12 to equal out the CO2 on the right side.
All right, so this is, wait a minute. We're going for oxygen, right? This was a miscount, wasn't it?
I did something really different, but
Yeah, we counted this one wrong. We needed 11 there to give us hydrogen, but now we have 11 plus 24, right? So we actually have 35. So we got 35 here. So now we got to go back and figure this again. We need 35. We've already got 11. So we need 24, don't we? Extra oxygens. So this would be what, 12? Let's see if that's right.
that's what I got. So.
Okay. So we got 1, 12, 12, and 11. Right. If we tallied right, that should be the answer. And let's see. Well, we're not finished yet. That's the first step. You have to balance the equation before you can equate moles of one to moles of the other. Now we have a balanced equation. All right, so now what was the question? How many moles of oxygen are required to react completely with 1.26 moles of sugar? 1.26 moles. We want to know how many moles of oxygen are required to react completely with that many moles of sucrose. So now we've just got a conversion problem. Once you balance the equation, those ratios are fixed. 1 to 12 to 12 to 11. And they cannot change. Except, well, this is the simplest whole number ratio. You could change them. You could multiply the whole thing through by 2 if you want. But that wouldn't be the accepted. You'd still have the same ratio, because instead of 1 to 12, it'd be 2 to 24, which is the same thing. All right. So the point is, once the equation's balanced, those numbers fix the ratios of moles to moles of each of the reactants and products, which is a good thing, because now we can take this number, I'll just call sugar, rather than writing that whole thing out. Now we need to find out oxygen. That's where we're headed, moles of oxygen. So we got to cancel moles of sugar and leave us with moles of oxygen. The numbers that go in here are derived directly from the coefficients. 12 oxygens, 1 sugar, right? So 1.26 times 12 will give us our answer. So I get 15.1. Okay, that one cancels there, leaves us with this one. Then all you have to do is say this one times that one equals that. Right, because this is in the numerator. We're good? Okay, let's see if there's one. Yeah, that is one of the answers. Let's see. Okay, so even if this was a bonus question, it was still doable with your current knowledge. You just had to not make the mistakes that I made. Okay, any others? I think I also have a review video from February, from last semester's class, that's posted in Blackboard. You may be working. We work from exactly the same document, but that class may have been more concerned with other problems. And if you take a view of that, you might see something in there that we missed in here. But this one will be posted also. Okay. Anything else? Or shall I ramble on? You might notice that in the key or the worked problems, this document, that there are some numbers are skipped. Like with this one, I skipped the first one, simply because there's no explanation for the first one. You just have to know it. Which of the following statements is not true of balancing equation? Yeah, sure.
I have a question.
About?
Never mind. Because I was gonna ask, like, would you do the oxygen separate?
Oh, no, let's look at that. 17? Yeah, that might be of interest to some other people. Plus, we're getting into another type of equation that uses polyatomics. Right? So this is a good place to jump into that one. So when you balance the following equation, using the smallest possible integers, you know, our convention, what's the number in front of the substance in bold, which is KNO3? Well, let's write that up there. And whoever designed this problem was kind enough to just give you the equations. Didn't put them in a word problem that forces you to write the balanced equations for each of the compounds. Okay. So let's, just for practice sake, let's just name these compounds. Okay. What is that? Polyatomic. The giveaway is it's in parentheses. The polyatomic is nitrate. Okay. It's a -1 charge. You've got 2 of them, so the total is 2 minus. So what does lead have to be? Lead has to be 2 plus. So this one is lead 2 nitrate. Okay, how about this one? There's another polyatomic. Carbonate. Carbonate is 2 minus. And this one is 2 of those. To balance it, 1 of these, 2 of these would be 2 plus, balance is 2 minus. So that means each one of these has to be 1 plus. But lead comes from this part of the chart, right? So we have to say what the charge is. Where does potassium come from? It comes from over here. It's always +1. So that makes it a type 1 compound. So all we have to say to balance this one, or to name this one, excuse me, is potassium carbonate. Okay. So if this were in a word problem, we'd say, balance the equation of lead nitrate with potassium carbonate to yield these two, which we're going to name now. And then you would have to go in and go backwards from this to that, that one to that one. Huh? You might get some. Let me see. I would expect at least just one, just to prove you can do it. Yeah, there's one in there. So this one would be, there's your carbonate, which is 2 minus. How do we know it's 2 minus? If you don't have it memorized, you look it up in the table. And that table will be on the test at the very end. It's right there. Common polyatomic ions. Anything that's in this review document on the back, additional useful information, it will be on the test. So just learn how to use it. And then that means with one of these and one of those, that has to be 2 plus. So the charge did not change. Right? Stay the same. So now we have lead 2 carbonate. And this one is nitrate again with potassium. So that makes it a type 1 compound. Okay, so those are the names of our compounds. That wasn't part of the problem, but I couldn't resist. Okay, so now let's go to balancing this equation, because that's the only way we're going to answer the question. The question is, what's the coefficient in front of that one? So here's an opportunity to use the other trick that I gave you. If you've got polyatomics on both sides and they remain intact through the reaction, treat them as a unit, right? Treat them as one of your balancing units over here. So we have lead, we have nitrate, we have potassium, and we have carbonate. Okay? And we know because they don't change. If you found nitrate here, and you found nitrate over here, but you also found nitrogen somewhere else without its oxygen, then you couldn't do that. You would have to split them up into their elements. And that would take a lot longer. So this is nice. And this also demonstrates what type of reaction. Toward the end of our last lecture, we covered this one. Double replacement. This one replaces that one. Right? They just swap places. This one goes over here and gives you the carbonate. This one goes over here and gives you the nitrate. Double replacement. So, and many double replacement reactions produce insoluble compounds. Right? So you would need to look it up if that were the question. You would look it up on that grid. It's also here. I just saw it. On this grid. And say, all right, lead 2 plus and carbonate. So lead 2 plus is over here, follow it down to carbonate. Here's carbonate. Here it is. It's grayed out. That's insoluble. So you would mark it with an S for solid. Okay. If that were the question. But in this case, we're just balancing the equation. Okay, so we do our tally. 1 lead, 2 nitrates, right, because there are 2 here, 2 potassiums, 1 carbonate. On this side, we have also 1 lead. Yes, nitrate, only 1 nitrate. potassium. And carbonate. Is that right? 1, 1, 1, 1. 2, 2, 1, 1. Okay. Now we can start the balancing act. No other rules actually simplify this for you. In other words, holding something until later, because they're all just a mix. So when that happens, I usually just start at the top. That one's already balanced, then I move to this one. So how do we balance the nitrates? We need a 2 over here, right? So that gives us 2 nitrates and 2 potassium. And we're done. That was too easy.
Right, I was doing them individualized, and I was like instead of keeping the electrons
Oh, you listed
together,
them? Oh, don't do that.
no, that's way easier,
Yeah, but I was like confused.
because I was like,
Yeah. Yeah, that's one of those, and I also included in useful information this balancing chemical equation hints. Yeah, it'll be there too. I don't know if you'll have time to use all the information, but it's there. Okay, so the answer to the question is 2, which in this case would be D. And then again, once you've established these coefficients, remember that's a 1. That's a 1. That's a 1. And that's a 2. We just don't write the 1s. If you've got the compound written, there's got to be at least one of them, right? So putting a 1 there is redundant. Okay. Any others?
What are you saying it's going to be
10 points. What type of question you mean? Well, let me see what I plugged in here for 10. I didn't. I went straight from 5 to 15. Okay, I'll give you an example of the 15-pointer, right? I mean, if you could get all that, that'd be worth a lot.
Do you have any lessons on it?
I'm sure I do. Yep. Let's look at one. It's actually an exercise in writing and balancing the complete molecular equation, and then taking that equation and breaking it out into its ions for the complete ionic equation, and then going from there to the net ion. So let's just do one slowly. Number 138. Okay. So here we're given, actually this, let me check something here. Hold everything, Dick Tracy calling headquarters. Okay, we're good. That's too far back. You guys don't remember that cartoon, do you? You do remember it? Dick Tracy. They said Dick Tracy called, and he pulled out his video watch. Yeah. Okay, so this is a word problem, and it says write the molecular equation, then the complete ionic, and then the net ionic equations from these compounds. Our reactants are copper 2 nitrate, copper 2 plus, right? This is number 138. Copper 2 nitrate. So nitrate has a single charge. That means you need 2 of them to balance that 2 plus. Okay? That's an aqueous solution. Now we're going to react that with sodium hydroxide. There's sodium. And what's hydroxide? It's a polyatomic. OH. So this is a +1 and that's a -1. We're good there. And this is also soluble. So what do we get out of that reaction? Well, actually, the problem tells you what it is. You could derive the products from this one because you know it's a double replacement. Copper replaces sodium. So it'd be, you would have copper and hydroxide, right? So this is 2 plus, and that's 1 minus, so we need 2 of these. Okay? And then sodium replaces copper with nitrate. So this one would be sodium nitrate. And that's all you have to write, because sodium is +1, nitrate is -1. Okay, now we have to decide, do we get a precipitate out of this? So one of them turned to solid. You have to look up copper against hydroxide in that table. Right? So we just turn over here and say, okay, copper is in the middle of the top row. Follow it down until we find hydroxide on the cross. It's grayed out, isn't it? Right. So this is a solid. How about sodium nitrate? If we go by rules, first rule says sodium is soluble. Second rule says nitrates are soluble. There's no conflict there. It's soluble. But if you don't go by the rules, you can just look it up. Sure enough, sodium nitrate is soluble. Okay, so now we have our written starting form. We know what the reactants are. We know what the products are. Now we just have to balance it. Okay. So we have polyatomics that don't change, so we can keep them together. Copper, nitrate, sodium, and hydroxide. Okay, so we have 1 copper here, and 2 nitrates, and 1 sodium, 1 hydroxide. On this side, we have 1 copper, again, nitrates, 1 nitrate, 1 sodium, and 2 hydroxides. All right, so coppers are already good. How do we get nitrates? We need 2 on that side, don't we? We'll put a 2 here. That gives us 2 nitrates, 2 sodiums. Okay. Now we need 2 sodiums on this side. So that gives us 2 sodiums, 2 hydroxides, and we're balanced. Typically, these double replacement type reactions, they balance very easily. Just like that, 1 or 2 steps and you're done. In fact, if you do enough of them, you can probably get to where you wouldn't need this part. You just look at it and say, bam, bam, done.
I learned this one at the beginning, and I teach myself.
Go in circles. That usually happens if you don't write these correctly.
Exactly.
Yeah, personal experience.
Personal practice. I'm like, okay, I totally screwed up somewhere, and then I'll go back and check.
Yeah, that's a good
And
indicator.
that's just missing a number, like.
Yeah, if you keep going in circles,
Mhm.
go back and check your compound.
And it's always the oxygen that I get stuck
Oh.
with. It's always the oxygen.
Okay, so now we got a balanced equation. Now we can answer the question. This is what you would put in the first 5-point part of the question. You know, this answer, that plus that, 2 of those, 1 of these, 2 of those. You would write in as your answer for the complete molecular equation. I should say just the molecular equation. Okay, now we want to write the complete ionic equation. That comes from recognizing that in solution, those are not compounds that hold together. In solution, they're separate ions, right? So how many of them do you have? Well, here you only have one copper in solution. You have 2 nitrates in solution. So notice that this subscript becomes a coefficient for the ionic equation. You have 2 of them. You got to count for everybody. You can't throw anything away and you can't create it, right? So you got to account for it. One of these, 2 of those. You have 2 sodiums and 2 hydroxides. Okay? We've accounted for all of our ions as reactants. And that's why they can react, because they're all in solution and they can interact. The ions are free to interact with one another. Yeah, you just bust them apart. This is the only one that you can't break apart because it's stuck together in crystalline solid form and it's not given up. So it drops out of solution. It's a solid. We leave it alone, right?
What do we do for gases?
For this type of reaction, I guess you could produce a gas here. If you do produce a gas, it won't be on both sides. That's the key. The gas that you produce in a reaction like this is only on one side. Keep it.
Don't break it either.
No, it won't break up.
It's only break apart.
The ionic compounds in solution. This one is written over here because it's a solid. It's removing itself from the reaction environment. Gases do the same thing, only they go the opposite direction. Okay, so that's a good question. You keep the gases too. I can't think of a reaction right off the top of my head where that would be valid, but no doubt there is one. And then the others, you have 2 sodiums. Let me see. So just a little bit more room here, so I can stretch it out. And 2 nitrates. So that's 5 points, that's 5 points. Okay, in our scenario. And that's the way you write your complete ionic equation. You've got to balance this one first, then you can write this one. Okay. Then what do you do to go to the net ionic equation? What do we look for? Starts with S. Spectators. Those ions are just sitting on the sidelines. They're not doing anything. They're just sitting there in solution. They're the same here as on the product side. Right? They don't react. In this form, we say they react by double replacement, right? But in reality, they're still in solution here and here. These 2. There and there. Same on both sides. That just means they stay in solution. They can care less what the other guys are doing. Right? So those come out, right? It's like if you have, in algebra, if you have A plus B equals B plus C, that's actually A equals C, isn't it? Because you can subtract B from both sides. Subtract it from that side, bring it over here, it's a negative, it's gone, right? So it's similar concept. If it's on both sides of the equation, it may as well not be there. Of course, in physical terms, they're still there, right? But we're focused on the reaction of interest is the one where the ions interact and produce a different phase. So these aqueous ions, copper and hydroxide, come together to form this solid. So that's our net reaction. And 2 hydroxide yields this one. Okay, and you can check yourself to see if it's balanced now. See, 1 copper, 2 hydroxides, 2 hydroxides. We're still balanced. So that's 5, 10, 15 total points available for that type of question. Okay. How about, before we get too far, let's look at identifying types of reactions. Those tend to give students trouble sometimes too. First of all, number 4, this is just to start slow and speed up. You're on the roller coaster and you're just coming over the crest. So let's take this one at the crest, and then we'll catch the others on the way down. Number 4 is all the following are clues that a chemical reaction has taken place, except, so you're looking for the one that's not a clue to a reaction. So we have A, solid forms. B choice is reactant is smaller. C choice is bubbles, gas forms. D is color change. And E is flame. Okay. So, if you paid attention in class and you studied, you probably can select the ones pretty quick that you know are indicators of a reaction. If you see a flame, you definitely got a reaction. Right? So we're looking for the one that's not. So color change, got a reaction there. How about gas? Yep, that's an indicator of reaction. Solid, I would say, solid reaction. So by process of elimination alone, we said that's got to be it. Because I don't have anything else down here like none of the above or 2 of the above or those kind of tricky selections. So that's the only one left. And as a matter of fact, reactant is smaller is not an indication that the reaction is occurring because you can't see it. Right? We're talking about what's happening on the microscopic level. Ask me, is the reactant getting smaller? I can't tell. That's not an indicator. I can't see, hear, taste, or touch to find out if the reactant's smaller. Now, if we had instrumentation that could measure the amount of reactant, you could use that. But we're talking about clues, right? We're not talking about quantitative measure. We're talking about clues. That means use your senses. So can I see something, hear something? We usually don't taste reactions. Not wise. Or feel like heat. That's okay. And with all those different clues possible, that one doesn't fit. Okay. All right. So now we know what we're looking for. Let's tackle some identifying some reaction types. Let's see. I think it's in chapter 7 we get into those. I'm looking for where they start in the review. I'm on page 31. Back up, be sure. Okay. Before we do that, let's get into this picture. That one up there. Because some of these graphic type questions are hard to interpret if you don't know what you're looking for or what the questioner's convention. All right. So this is 97. How we doing on time? Okay, we're good. So for 97, do I have to draw these out? Yeah, might as well. Okay, for 97A, and of course, this is an artifact of the way Word generates lists. The A is going to be the lower left corner of what it applies to when you stick an image in there. So don't think A is to the one below it. A is to the one above it to the right. Okay, so A is this one, where you have a calcium 2+, and a chloride and a chloride. Okay. So that compound is in aqueous solution. Calcium chloride. You got 2 negatives, 1 positive. Right? So that's the mole ratio of this compound in solution. 1 calcium, 2 chlorines. Right? The other solution has potassium, 2 potassiums, and 1 sulfate. Right? So that's also a proper ratio. 2 pluses and a 2 minus that it balances. These are aqueous solution. Now, what it's saying is, when you put them together, this is what you get. Try to put them in the same positions. And this one. Okay. So let's look at the question again. Which drawing best represents the mixing of aqueous calcium chloride with aqueous potassium sulfate when they are mixed in stoichiometric amounts? What do we mean by stoichiometric amounts? They are mixed in the exact ratio of the balanced equation. Coefficients, like 1, 2, 1, 2, whatever. Those ratios are stoichiometric. That is, you have exactly the right amount of reactants to where there's nothing left over. Unless it shows up on the other side. And then it shows up in the same ratio. So this is written correctly, that's written correctly, that's good. They're in solution. Aqueous solution. Over here, the question is, if we take that calcium, put it together with sulfate, what do you get over here? Calcium and sulfate, look at your chart, see, does it form a precipitate? Yeah, forms a solid, right? This says they're in solution. That can't be it. Because this one and this one form a solid. Okay, so if that's true, and we're looking for that solid, how does the questioner represent a solid? It's that black stuff at the bottom of the bowl, right? So in that case, we can go straight from this one to one of the ones that has the black on the bottom, which means that E is out. So we can narrow it down to B, C, or D, and then we just look at, well, one other way is to look at the reactants again. This is an accurate representation of the reactants. So we can look at the reactants for B, C, and D. And see if they're correct. Well, B is the same, right? You've got 1 calcium and 2 chlorines. You've got 2 potassiums and 1 sulfate for B, so that's good. So then you can look at this one over here and see what you've got. Well, we've got a solid on the bottom, it says. Right? It writes it out there and just does that. And then what do you have left in suspension? I mean, not suspension, in solution. Well, we've got a chlorine, got a chlorine, got potassium, got potassium. Now, is that true? Well, you started off with 2 potassiums, you ended up with 2. You started off with 2 chlorines, you ended up with 2. So that looks like the right answer. Right. If we go down to C and look at it, the reactants are wrong. That one's wrong, and that one's wrong. Right, so you can stop there for that one. D, that reactant is good, and this reactant is good. So if you get to that point, then you have to look at the product. So the product says you have solid on the bottom, and you have sulfate in solution, calcium in solution. That's wrong, because we know they precipitate. Okay. So that's how to read, that's how to interpret those figures. Now we can look at reaction types, try to identify them. And this is going to involve also some test-taking techniques. Because with a multiple choice question, the only possibilities that you can assign to a reaction type are the ones that you're given. Right? You may identify one that's not there, but that doesn't count because it's not one of the choices. Okay? Just a word of advance warning. So let's look at the first one we run across is 99. Classify the following reaction. And I think any reactions that are actually written out in this section are already balanced. Multiple, yeah, multiple choice. Do you need a?
Yeah, I left mine on my desk.
Yeah, I got a copy. Here it is. There you go. I'll use that one. So our reaction for 99 is this, and it produces this plus this. Now, this is one, the driving force for this reaction we didn't cover in that previous question, right? Probably because you can't see it happening. So it's not really a clue. But for this type of reaction, we've got an aqueous solution yields an aqueous solution plus the formation of water. If you form water in a reaction, that drives a reaction. But it's not technically a clue because you can't see it being produced. Okay, that's why it wasn't in that question. But that is a driving force for this reaction. Now, what type of reaction is it? Right, there's an acid, there's the clue, there's a base, right? So it's an acid-base reaction. Now, all these other selections, oxidation reduction, well, here's another way to tease that out. Did I put it in here? Yeah, I did. That little flow chart. If you've got an acid-base reaction, right, it branches off of here to the right. It's all by itself. It won't be anything else.
On the test, when we come to the one that's more than one choice, we got on there more than one choice, and that's why you'll have that on there. But we need this.
Like 2 of the above.
Yeah.
Well, right. Technically speaking, 2 of the above doesn't count here because there's nothing above it, right? If we're picky. Right, that's an acid base only. And you can look, there's no precipitate there. There's no combustion because we didn't add oxygen, right? There's no oxygen as a reactant. So that cuts out combustion and precipitation. Oxidation reduction, well, if you just look at oxidation states, the rules for oxidation states, remember those? Right? This is going to be +1. This is going to be plus because that's the ion charge. There. Hydrogen's plus, 2 minus for oxygen. Those are the accepted values. Didn't we do oxidation states in here?
When I have an oxygen by itself, that's.
This one, oxidation state 0. If it's an element, oxidation state is always 0. Am I getting ahead? Have we not covered that yet? Oxidation states?
We might have touched it.
We had to do some because in order to do redox reactions, you need to know what the oxidation states are. We didn't do that? Okay. Well, then you have to use that flow chart, right? If you see that it's an acid base, that's all it can be.
How do you know it's an acid?
That's an acid. See that hydrogen sticking out there in front? That's a base. See that hydroxyl? Okay.
If it was an oxidation reduction, you would have like an oxygen by itself.
If you had an oxygen by itself on one side and in a compound on the other, that's definitely redox.
And then it's a precipitation. Like I can, now I can kind of see which one's which. But if you just want to do a precipitation, would that also be the single comparison?
No, precipitations are double replacement.
Yeah, it's associated.
Let's take another one. Here we go, 100. Let's just take them in order until we start repeating ourselves, and then we'll skip one. This one plus this one. Bromine at room temperature is a liquid. Remember when you filled out that periodic table? You did it. And I asked you which ones are liquid, right? There were only 2 of them, right? That were liquid at room temperature. That one and that one. The ones you had to write in blue. Okay, so we have this one. And that's, in this reaction, that's a solid, potassium bromide. Now, what type of reaction is this? Here's the clue. Element, compound, redox. A as your choice is oxidation reduction. Okay. Then you can look at the others and say, is this a double replacement? No, because those are not compounds. You can't replace anything. Right? Replacements require you have 2 compounds on this side in order for the replacement to take place. Can't be a double replacement. Precipitation, the only way you can have precipitation is you have aqueous solutions on one side and a solid on the other. Single replacement. Single replacement requires an element and a compound together, where the element replaces one of the members of the compound. We don't have that either. Okay. Acid base? No. There's no hydrogen there. There's no hydroxyls. Right? So by process of elimination, that's the only one that is. Just A. For 100.
And you said precipitation would have aqueous on one side and what on the other?
And you're solid on the other side. Usually, it's going to be a double replacement, so you have aqueous, solid, and usually aqueous. On rare occasions, you get 2 solids. but usually it's just one solid and aqueous. Let's see. Skip 101 because we're trying to identify reaction types. 103. Let's do this one. Okay, so here's our equation. 2 carbons and let's see, fluorine, right? And it produces, oops, my mistake, cesium. Cesium chloride. So just out of curiosity, where does cesium come from? Over here. It's in the same family as sodium and potassium. I'm sorry? Alkaline metals, yep. Alkaline metal with a halogen. You can be pretty sure this element with that element is going to be extremely violent reaction. Maybe even you could just bring them together and they go at room temperature. Especially if they're that far apart, way down here, way up there. Those two are going to be violent reactions. Whereas if you had one that's maybe up here, like lithium and fluorine, you might have to say use a striker or a match or something to get it going. But it would also be a violent reaction. Exothermic, give off a lot of heat. But this one definitely will. So you don't want to do this one at home. All right, what type of reaction is it? Well, we have selections. Just A through D. This one's redox. This one's combustion. This one's synthesis. And this one's decomposition.
You're kind of losing the gas.
Say again?
Like the way I'm kind of reading it, losing gas.
Now, decomposition requires that you go from more complex to less complex. So it won't be a decomposition. Yeah, it's a synthesis, right? That's one. Decomposition is the opposite, so it can't be both. Right. It's not a combustion, right? But, right. But you have an element here and a compound there. It's redox. So it's synthesis and redox. So that's a case where we have two that satisfy the conditions of the reaction. So what do you do on a test if you run into that problem, right? There's only one space. Are you stuck with only one letter that you can put in? No. Just put both letters, right? Okay. So let's just take them in order. Now, 104. Here we go. We've got sodium sulfate, which is soluble, and lead 2 nitrate, which is soluble. Yield lead 2 sulfate, which is not soluble, plus 2 sodium nitrates, which is soluble. Okay. So what are our choices? Well, in this case, you only have 3 choices that are given. You have redox, you have acid base, and you have precipitation. So, is it a redox? No. Sodium stays the same on both sides, +1. Sulfate's the same, it doesn't even break up. So you can, the polyatomic, if it stays the same, that means the oxidation state of each element within it stays the same. It hasn't been touched. Lead stays the same. It goes from 2+ balancing 1- to 2+ balancing a 2-. So it hadn't changed either. So it's not a redox. There's been no transfer of electrons. It's not B because there's no hydrogen, there's no hydroxyls. So by process of elimination, plus the fact that you have aqueous, solid.
I don't know. I feel like this will help me better. Can you tell me the redox? What is,
Oxidation reduction,
yes, what does it have to have? for it to-
transfer of electrons. You have to show transfer of electrons. And if you want to know which way they go, just remember does everybody remember the mnemonic? Right? Oxidation is loss. Reduction is gained. And that refers to electrons. So anything that is reduced gains electrons. Anything that is oxidized loses electrons.
So in something like that, you just see change electrons.
The electrons move, yep. And that previous one I already erased. We had cesium was an element, right? And fluorine's an element, but in the compound, fluorine takes on a -1 charge. So it goes from 0 to -1. It gains electrons, it's reduced. Whereas cesium loses electrons to fluorine. Cesium becomes a +1 charge. So it goes from 0 to +1. It lost electrons. It was oxidized. And these always occur together. Never apart. You can't have one without the other. Okay. So let's see if I can find one we haven't touched on yet. Oh, 105. Let's do that one. So here's our equation. We got ammonia gas. We got oxygen gas. Produces nitrogen monoxide. Okay. Both nonmetals, so we just say how many there are. Nitrogen monoxide. And dihydrogen oxide. Okay, so this reaction of what are our choices? This one is redox is the first choice. Second choice is combustion. Third choice is synthesis. And last choice is decomp. Okay. Is it a redox reaction? Right. You go from an element to a compound. Actually, 2 compounds for oxygen. Ends up in both of them. So that one's good. How about combustion? Right. If you've identified it as a redox, then look for oxygen, and it's a combustion, because combustions are all redox reactions. Is it a synthesis? Well, technically no, because you're going from a compound element to 2 compounds, and we generally don't count that as a synthesis. It would have to be 2 elements to a compound. At best, this would be considered well, it wouldn't even be a replacement. No, it can't be either one of these. If we had something like this, that to produce, let's see, what would we produce? Well, produce that, you know, put these two together, that would be a synthesis. And if we had this and we drove the reaction backwards, that'd be decomposition.
Also, the decomp will have that error back.
Yeah, if you flip the reaction around,
But I mean, like,
Like two in, or,
now written that way, that's only a synthesis. If I flipped it around and flipped this over here and those over there, that would be a decomposition.
remember Randy had the line backwards.
No, not at this point. No. That's just to illustrate that all reactions are reversible. You can go backwards. Sometimes you have to force them. They're spontaneous in one direction and non-spontaneous in the other. Which means you have to put energy in to get them to go backwards. But it is possible. I think what I try to do for this class is decompositions are going to be element, element, compound. Synthesis, element, element, compound. Decompositions, compound, element, element. Just to keep it simple. Let's see if I can find one that's, yeah, there we go. How about this one? 119. So here's our reaction. Yields. That one's a violent reaction too. In fact, at one point in history, this was the basis for matches. Now they're different. Right? So there's your phosphorus element with the oxygen element produces this, what? These are both nonmetals, so we had tetraphosphorus decoxide. Okay, so what are our choices? 119. So A is redox. B is combustion. C is synthesis. And D is decomp. All right. Let's work from the bottom. Is it a decomposition? No. It's a synthesis, right? Two elements, a compound. There we go. Combustion, yeah. Oxygen. Redox, yeah. Element, compound. So it's all three.
what is an element in a compound? I know that sounds silly, but like,
I think on the left side, you just have like,
Just one symbol.
just one, and
Mhm.
then a compound is one together. Oh, because, okay.
Right.
That makes sense.
it's got like a number in front.
Yeah. Most elements on the periodic table can be represented by their symbol, like my favorite, gold. Some of them, though, come in associations with one another, like the diatomics. That's still an element. And then others, like phosphorus, it can take several forms. It can be like this. Another form is like that, right? It's still the element. But when you have situations like this, where you have just the element, but it has different numbers of atoms associated with one another, then you have what we call an allotrope. So these two are allotropes. They're still the same element, they just take different forms. The most popular allotrope is carbon. Right? You can have carbon graphite is one association. You can have carbon diamond. That's the most popular for most people. among scientists, the most popular is, right now, nanotubes. And then the first really complex arrangement of carbon that wasn't here was Buckminster fullerene. And it had 60 carbons together in a ball. So they called it a buckyball. Okay. So those are all allotropes of carbon, but it's still carbon. That's an element.
I thought they were called isotopes or isotopes, or.
No, they're not the same.
So they're different.
They're different, right? Neutrons. Right. Change the number of neutrons. So for carbon, these are allotropes, but these are isotopes.
Oh,
Okay.
okay. Now I get it.
The mass number is different. Now, they each have 6 protons, right? That's why they're carbon. But they have different numbers of neutrons, which makes the mass number different. So this one has 6 neutrons. This one has 7 neutrons. This one has 8 neutrons. Same number of protons in the nucleus. Yeah, they sound alike, but they're not. Okay. Any others that, in the process of doing all this stuff, any other questions that popped up? Just be sure you can balance equations. It's very important for this exam. Identify the equations. We went over a biggie. Right? You can write the complete double replacement reaction, then the molecular equation, excuse me. Then you can write the complete ionic from that, and you can write the net ionic. That would be valuable points. Identify reactions like we just did. The difference, that only comes from practice. Let's see if I've forgotten anything. Balance equations. What types of equations? Just scan, see if I got anything else that's worth talking about. You might want to just glance through the chapter for scientists, significant scientists that contributed to these things. For instance, who discovered the essential nature of acids through conductivity? Arrhenius. Arrhenius did that. He did a lot of other stuff, but that we won't get to in this class. But general chemistry students, they're privileged with having to live through the Arrhenius equation. I don't see anything else that just really pops out at me. Number 26 is another bonus type question where you're given in a word problem, ethane is reacted with oxygen and produces carbon dioxide and water. So you're told what the compounds are. Then you write the equation, balance it, and then use the balanced equation to answer the question. How many moles of oxygen for every 2.43 moles of ethane? So it's just like the sugar combustion, right? You didn't know you could burn sugar, did you? Yeah, you get a teaspoon of sugar, and you get a flame, heat it up pretty good first. You get melted. It'll
Sure,
melt.
you know, the lighter just kind of sprinkle on doing it.
And it'll combust. It's an organic compound, loves oxygen. Right? That's combustion. In our bodies, we do something similar, only we do it slower. Because if you combust it in air, it gives off a lot of heat all at once, and most of it's lost. Right? So in our bodies, we take those steps and we break them out into like 100 different steps. And each one mediated by an enzyme. And you go from this step to this step. And each time you go, well, not every time, but periodically in there, you bleed off that energy and you store it in a compound like ATP. Everybody knows what ATP is, right? It's your body's currency, energy currency. Adenosine triphosphate. No, you haven't had that anatomy yet?
I know ATP is, right?
Yeah,
I had
ATP.
it like
Fancy name.
Okay, so the reason we do it that way is so that we just don't self-combust, right? If you burn sugar or glucose, one of those compounds, the way we would in chemistry, then you just ignite, you just burn up. There's too much energy at once. So we take it through steps and periodically we take that energy and store it someplace. So the steps are smaller, that means the heat expenditure is lower, so you don't kill yourself. And those reactions, they always produce, they're never 100% efficient. In other words, the energy that you extract from the reaction is not all of the energy that's available. Right? It's not 100% efficient. So that extra energy that you don't grab at that step goes into heat. Right? It's just thermal energy. That's why our body temperatures are 98.6 or 37 centigrade, because of that extra heat that's generated. And that's not a bad thing, because enzymes are biological catalysts and they work best in a very narrow temperature range. So if your temperature range goes outside that 37 degrees, like goes too low, you go hypothermic, or it gets too high, hyperthermic fever, then those enzymes start not working, right? Sometimes they just completely break down, and if you go far enough, of course, that'll kill you. So that's why fever or hypothermia is bad.
I was wondering about questions 75 and 80. They're
Okay.
both concept kind of questions instead of
Okay,
formula questions.
75. Let's see what 75 talks about. 75. A substance, when dissolved in water, produces a solution that conducts electricity very efficiently. So it's a conductor in solution, right? And it's very efficient. So by definition, if it conducts electricity in aqueous solution, it is an electrolyte. If it's very efficient, then it's a strong electrolyte. Okay, so then you look down here and say, okay, strong electrolyte is D. And you said 80 was the other one?
Yeah.
Okay. Factors that most commonly cause chemical reactions to occur are all the following except. Oh, this is kind of like that earlier one we did. Okay, that's
I did
fine.
the process of elimination, but I would step between A and B.
Okay, so you've eliminated as we're looking for the exception to them, right? So C, D, and E are all drivers of a reaction, right? Formation of water, gas, or solid, right? So we're trying to decide between a decrease in temperature versus transfer of electrons. Anytime you transfer electrons, you're driving a reaction. So a decrease in temperature does not commonly cause a reaction to occur. So that's the one you're looking for. And in fact, the vast majority of reactions go slower when you decrease the temperature. There are some exceptions, but as a general rule, you decrease the temperature, the reaction is going to slow down. And there's a rule of thumb. That I've learned this rule of thumb in biology class. Chemists didn't give it to me. They either didn't know it or didn't care. Is for every increase of 10 degrees centigrade, a reaction will double its rate. It go twice as fast. So if you increase the temperature 10 degrees, now this is for reactions. It's a narrower range for living systems because of that thing I gave you before, enzymes. If you take the temperature too high, then you denature the enzyme and the reaction just goes like that. But in general, if you increase the temperature 10 degrees, it doubles the rate of reaction. Now, that's a rule of thumb, right? So it may only 1.5 for some reactions, or it may go 2.5 or 3 for other reactions. But as a general rule, so 10 degrees up, you double reaction. What happens 10 degrees down? Cut the rate in half, right? So if we go 10 more degrees, we cut it in quarter. 10 more degrees, 8. So it's powers of 2. So that's why we store cell cultures in liquid nitrogen, because it's minus 195. Right? So if you're starting at room temperature, say 20 degrees or 25, right, that's okay. And you go down how many times? I don't see 10, 0, keep going. I mean, you've virtually put a permanent halt to reactions at that temperature. So that's why storing cell cultures at that temperature will preserve them for indefinite period of time. Sometimes they go into the liquid with these little vials, cap vials with your samples in it. Sometimes that's too cold. So then they go to vapor storage. And vapor storage in this is like minus 100 degrees. That's as cold as you can get. So they just store them in the vapor above the liquid nitrogen. It's not as cold. But it's all based upon that principle. Is make them cold and slow the reaction down. When we collected samples in the field, we couldn't carry liquid nitrogen with us. It's just too much. Okay? So we carried coolers with dry ice. Okay? So dry ice is minus 78.5 degrees centigrade. That's cold enough. Take your samples, put them in a sample bag, usually made of Tyvek with lots of holes in it, and then label it. And then you put that bag in your cooler on dry ice, and it freezes pretty quickly enough to keep it from decomposing. Right? And you keep it there, and then when you get to where you're going, you either put it in the freezer. We had freezers that would go down to minus 100 degrees centigrade. Or if you really wanted to, if you're going to do something else with it, you could then submerge it in liquid nitrogen. And most of the time we freeze dry them. Everybody seen a freeze dryer? Freeze dryer. You know Sanka coffee? That was the first commercial product that was freeze dried. They take coffee, they put it in a chamber, right? They freeze it first, put it in a chamber, and then evacuate all the air. So when you take the air out, the pressure drops, then the water goes straight from solid to gas. Right? That's sublimation. So it goes straight from solid to gas, and it leaves the cells intact, or it leaves the compounds that were dissolved in water still in there, but it doesn't damage them because it's so cold. Right? So you get this like this big brick of freeze-dried coffee, and then you run it through a grinder. And if you drink coffee, you look at Sanka, they got these little angular chunks of coffee. And all you have to do is take those and dish them out, throw them in your hot water, and there you go, instant coffee. Supposedly, it preserves all the flavor compounds without decomposition. But the key is to stop the reactions. Right? We wanted to freeze our samples because once you detach that plant tissue from the plant, the cells start to die because you've detached them from their source, right? From the water flowing up and food flowing down that they produce. So you stop that, and pretty soon those cells start to die if you don't do something. So we freeze them. It stops their reactions cold. So you don't get any further decomposition reactions. They call it post-harvest physiology. And there's a whole science behind that. That's how you can keep your vegetables, fruits and vegetables in the grocery store. Think they're fresh? They might be a week old. But the technologists that pulled them from the field knew how to treat them so that they wouldn't decompose on the way. Various things you can do. You don't want to freeze them, right? But you do want to keep them fresh. So for instance, bananas that come from Central America, they pick them green, right? These big stalks. They pick them green, put them in the containers, and while they're in there, they continuously evacuate the gases because as they age, they produce ethylene oxide. And ethylene oxide causes a maturation. So the bananas will turn yellow on the way. Well, if you let them turn yellow too soon, then they start to rot. So they just keep evacuating that ethylene oxide, and it keeps them from maturing until the ship gets between maybe 2 or 3 days out from port. Then they actually start pumping ethylene oxide back in to get the rapid maturation. So they go from green to yellow really quick. And there are a few of them that have the green tinge. If you go to the grocery store and try to buy bananas, they'll bring them to you with just a little bit of green left so that they can finish maturing on your counter in your kitchen or on the hook. Those fancy little things. They got cantilevered hooks you hang your bunch on. Keeps them from sitting on one side. Because if they sit on one side, the air can't circulate there. So it matures faster than the rest of them. So you get these dead spots of your bananas. You don't eat them fast enough. I just put them in a basket. That lets the air flow.
Which proves that there's a lot of science that goes into everyday things.
Oh yeah. Yeah, people, they make a living at it. Let's see, are we out? Oh, we are out of time, sorry. So we'll see you Tuesday. Stop this thing and let it